Good morning. Today we begin a new chapter. In this chapter, we shall learn about some of the defects which are present in crystals, particularly with respect to metals. And last class we had seen that the process of deformation takes place in metals by process of slip and twin. And we also calculated that if the crystal is perfect, it does not have any defect. In that case, the stress required to cause slip in a crystal is very high, but in reality the metals deform at a stress much lower than the ideal resolved shear stress. And the reason for this lies in the fact that crystals are never perfect, it has defects, and in this chapter we shall learn about the types of defects which are present in metals, metal crystals, and how and what is their effect on properties. So, broadly we will consider point defects, primarily some vacancy, some interstitial atom, some substitutional atom. We will also try and find out why it is necessary to have vacancy in metals, and there is a relationship, I mean how much energy is needed to create a vacancy. We will look at some line defects. They are known as dislocations. There are two broad types of dislocation, edge and screw. We will also learn about surface defects like stacking fault and what causes stacking fault. So, that means this is also associated with formation of a different types of dislocation called partial dislocation. We have already talked about grain boundary. This is also a type of defect. There are different types of grain boundary. We will try to know about it in a little more detail. We will also look at dislocation interactions and some of the dislocation mechanisms for strengthening. We will look at the Hall-Page relationship, which defines the strength of metal as a function of its grain size. Now, let us look at point defect. What is it? Now, one of the common point defect is vacancy. So, crystal is an array, periodic array of atoms, which is shown over here along this line, but often it so happens some of these atomic positions are not occupied by atom, like here. This is a vacancy, this is a point defect, and sometime we try to push another atom. It is possible when we do alloying, if an atom is very small, it can be accommodated within this interstitial space, the gap within the lattice, and if the this atom is large, say something like here, it will try to push these atoms apart and cause a strain field. Now, why do we have vacancy in crystals? Now, this is we can look at it like this. We can assume that vacancy to be a species, and say basically we can think like this, that this system is a mixture of atom and vacancy, and as the concentration of vacancy increases, definitely the stability or energy of the system will change. And we know that stability of any system, it has been introduced, is defined in terms of free energy, which is written like this: free energy is equal to an energy term, internal energy H or enthalpy, minus T is the temperature times entropy. The entropy is a measure of disorder. So, basically what we can look at it, that if this vacancy they are arranged, they can be arranged at random, and this causes a disorder in the structure. You increase more vacancy, you increase the disorder. So, therefore, that disorder increases, the entropy of the system increases. And basically, if we look at the total overall that energy, that nature, if you want to create a vacancy, you have to give some energy, and if you want to create more vacancy, you have to spend more energy. So, H is moving like this, and this entropy increases with the disorder, but the overall effect here it is minus T S. So, basically this is negative, this decreases like this, temperature times entropy decreases like this. So, therefore, the total energy of the system will have a nature like this. That means, this axis is the energy, this axis is the concentration. So, there is an equilibrium, some concentration of vacancy. This determines if the vacancy keeps on decreasing, the system become more, a vacancy keeps on increasing, the free energy decreases and it attains a minimum somewhere here. So, this is the stable configuration. So, this is, one can say that this is the equilibrium concentration of vacancy in the system. Now, it is possible to calculate or find out the concentration of vacancy in a lattice, and here this is a very simple case where you can apply the principle of statistical thermodynamics. Now, entropy, one of the major factor contribution of towards entropy is how these vacancies are arranged in the lattice. They will be arranged in random, arranged at random. So, you can think about two spaces, one is the atom and another is vacancy, and if there are n sites, n total number of sites, out of these parts say n is atomic sites, sites occupied by atom, and NV is the site occupied by the vacancy, and total number of site is equal to n plus NV. So, with this kind of case, if you try and arrange these two species, so then what you will get, the way you can arrange them is given by this. This is a case of simple arrangement, permutation, combination problem. So, if you have, this is the total number of atom which is can be arranged in factorial NT ways, and since these atoms they are indistinguishable. So, this is NT minus NV is the number of vacancy, this is the number of atoms. So, they are totally indistinguishable. So, therefore, number of arrangement is reduced by this factor factorial, and this is the way this number of vacancies are also indistinguishable. And here that entropy has a relationship with the way these arrangements can be made, and which is shown over here. Entropy is equal to K times log to the base E ln ln W. That means, way this arrangement can be made, and usually these numbers are very large, this factorial whatever we consider is a very large, and there is an approximation approximate way of calculating such large factorials, which is known as Starling approximation, and using this approximation one can write that ln factorial x equal to x ln x minus x. So, if you apply this approximation, and then you can derive an expression for entropy because of this way the vacancies are arranged, and which is shown over here. And with a little algebraic simplifications and with some approximation, like this n is much larger than NV. So, in cases wherever some cases you can n plus NV can be approximated as n. So, basically with this it is possible to show that this entropy is equal to this, and which here this gets cancelled. So, therefore, this is N V ln N minus N V ln N V. So, which is written here. So, therefore, you can, this is the entropy part of the free energy expression, and also to create a vacancy you need to give some amount of energy which is Q V. To create one vacancy you have to spend, or you have to provide necessary activation, and this activation energy is Q V. So, this is the total expression for F, and you can try and minimize, find out at what value or what magnitude of NB F is minimum. So, the best way you can do it, you differentiate it with respect to NV, which is shown over here, and then equate it to 0. And therefore, it is possible to show approximately that number of vacancy will be equal to n exponential q v by k t. And maybe you can try as an exercise where T is the absolute temperature, K is the Boltzmann constant. So, this is Boltzmann constant is known, and suppose for a metal, say suppose take copper, and you will find that you try and find out its number of vacancy, and say this can be around 100 kilojoules per mole, Q v could be around 100 kilojoule per mole, and therefore, you can try and find out in 1 cc of say metal copper what will be the number of vacancy at say temperature, room temperature, and another at say 1000 degree Kelvin. And you will find out, since because of this exponential nature of this temperature dependence, you will find that vacancy at higher temperature will be several order of magnitudes more than that at room temperature. Now, there can be another type of point defect we can think about. We often mix metals, so which is known as alloying, and primary purpose of alloying is to improve its properties. Like we know the silver is very soft, if you mix it with a little amount of copper, it makes it hard. So, which is actually known as sterling silver. And when you mix up this atom, where does this atom go? Now, which is pictorially shown here. So, they can go, there are two sites basically. See, one here, say suppose this is a metal A and this is red is metal B. So, if you add a metal B some amount, what it can do? It can replace some of these atoms from its normal site, and it is substituted by metal B. So, this type of this also we can consider, because that arrangement it disturbs that periodicity. So, this also is a defect, this is also a point defect, and we call this type of defect, you can say that this is a substitutional impurity atom, and we consider it as an impurity atom, and we call this as a substitutional solid solution. Now, pure metal, as has been mentioned, is soft. An addition of alloy element makes it hard. This example I gave is that of sterling silver. Now, what are the factors which will determine how much atom you can take, a particular lattice can dissolve how much amount of another metal? This will primarily determined by the certain properties of the two, or certain characteristic of these two metals, and these factors which are listed here. So, one is atomic size. If this atomic size is nearly same, you will find the very large amount of, you will find that the two can mix in possibly all proportion, or say the large amount of second element can be taken into solution. Say which is say shown here. So, this atomic dimension is same. So, there is no lattice distortion. So, in this kind of setup, a large amount of second element can be dissolved in the matrix, but which is very rare. Always you will find there is some amount of difference in size. So, when a larger atom is put over here, it will try and displace and generate a strain. Similarly, if this atom is little smaller, these atoms also get pushed. So, here also the lattice around the atom will get little disturbed. So, there will be some amount of stress field surrounding the solute atom. Next factor is the crystal structure. So, if the both crystal structure is similar, then they can have large amount of solubility. Like you say that case of silver copper, silver is FCC, copper is also FCC. So, here there is a substantial amount of solubility, but take the case of let us say iron. Iron is a BCC structure, and say suppose if you mix it, you add some amount of nickel to it, nickel is FCC, or some amount of copper to it, copper is FCC. So, here definitely because of the difference in crystal structure, they will have limited solubility. Another important factor is the valency. If the valencies are different, in that case there will be a tendency to form compound. So, if the two element valencies are different, so instead of forming a random mixture of the two, you will try to form an ordered phase, or in extreme case it can form a compound. Similarly, electronegativity is also quite important, and basically if we look at that molecular structure, I mean if we can extend it to solubility in liquid phase, we know very well water molecules, they are polar, and therefore, it can dissolve any other polar molecule. So, that has to be some amount of similarity between the two. So, water can mix with let us say some other polar molecule, say like say it can dissolve possibly that acetic acid, but if you try and mix with octane or petrol or these kinds of which are not polar, they won't mix together. So, situation is something similar in solid as well. The two species should be nearly identical, then only one can dissolve the other. Next, we look at another kind of mixing or the way these impurities can be present in the lattice, which is shown here. This is called interstitial solid solution. This also is a case of a point defect. Say suppose the second atom is very small, it can be accommodated within the lattice. So, in that case we find to put it here, definitely in very rare cases, I think we did some of these, solve some of these exercise. Say let us look at a case of iron lattice. Iron exists in two different crystalline form. At a low temperature or room temperature, iron is a body centered cubic, and body centered cubic structure has certain types of interstitial site, and face centered cubic structure has also similar interstitial sites, and dimensions of these, I think we did some calculation, some exercise were given, and if you look at that, you will find that atomic radius of carbon atom is 0.075 nanometer, whereas if you try to calculate the radii of interstitial sites of that BCC iron, that is alpha iron, this is of the order of 0.036. So, there is a large difference. So, if there is a BCC lattice, if you try and push this here, there will be large distortion around the place. So, this puts a limit. I mean, so that means whereas if you look at the other one, face centered cubic crystal, the radius of this interstitial site is much larger, 0.053. It is substantially larger than this, but still it is smaller than the radius of carbon atom. So, therefore, even if here a carbon atom goes into the interstices, it will cause some amount of lattice distortion. So, therefore, interstitial solid solutions definitely there will be some limit to solubility, and this will be determined, it will be primarily depend on the atomic size or size difference. And it will be interesting, I think you can again go back to your earlier lectures and look at, say, we did calculate atomic packing density for face centered cubic crystal. Here the packing density is 0.74, whereas BCC the packing density is 0.68. So, yet face centered cubic crystal has higher solubility of carbon. Why? I think apparently this may look like a fallacy, but if we look at a little more carefully into the way these interstitial sites are present in BCC and FCC. So, basically BCC maybe the packing density is little less, but what is more important, the dimension of these interstitial site, the octahedral site you try and calculate in case of which is little larger. So, it will be the atom will primarily, I mean carbon atom will try to go into the octahedral site, which is bigger than tetrahedral site. And if you try and calculate this octahedral site in FCC and in BCC, you will find this octahedral site is bigger in FCC than in BCC. So, but BCC does have another tetrahedral site also, which is much larger than FCC, but it is size of this tetrahedral site is smaller than octahedral site. So, therefore, the solubility of carbon in alpha iron is very limited, and as we go along we will find that gamma iron, which is an high temperature phase, can dissolve up to around depending on temperature up to 2% carbon, whereas solubility of carbon in alpha iron is 0.02%. So, substantially several order of magnitude lower. Now, let us look at origin of vacancy. So, obviously, when we calculated that number of vacancy which you can get under equilibrium at a particular temperature, we implicitly assume that to create a vacancy you have to give some amount of thermal excitation. So, thermal activation is one. Another, you can bombard this metal with high energy particles like electron beam, ions, neutrons or X-ray. In that case also you will be able to push an atom from maybe from here to here. So, this case is, so this is the way from if you bombard it with an atom or give some thermal activation, one atom, it moves from the center, it comes to the surface. This type of defect is known as Schottky defects, and in this case you can easily see that when this atom comes here, apparently it looks that its volume is increasing. So, that means its density is decreases. So, therefore, this could be a method of finding out the vacancy concentration in metals. Later sometime we will see how this can be determined. So, so looking at this mechanism of formation of vacancy, it says it offers that one way of measurement could be density. Another, similarly, you can also see there will be some changes in lattice parameter, also dimension also can change. So, from that X-ray also it is possible by calculating lattice parameter, effective lattice parameter, also you will get some idea about the vacancy concentration. There is another way a vacancy can be created. You can try and push an atom from its normal site to interstitial site. This is called Frankel defect. Here, of course, the overall way it is formed, you find that overall there is no change in volume. So, therefore, here there is no change in density, but definitely there will be lattice distortion. So, but obviously, the interstitial sites are much smaller, you need much higher energy to create this kind of defect. Now, if you have vacancy in ionic crystal, situation is little different. Say basically, say you can have two kinds of ionic crystals, say one where they are stoichiometric, that two both positive and negative ions, they are present in equal proportion. So, therefore, overall it is neutral and exactly like NaCl. Valency of sodium is 1 plus 1 and chlorine is 1 minus. So, therefore, so this has a negatively charged ion, sodium is a positively charged ion, and their attraction is the main bonding strength, and here pictorially it is shown over here. So, if in a lattice, if you have one chlorine ion missing, so that means it disbalances the overall electronegative or charge of the material. So, therefore, to compensate that, another sodium atom should also be displaced. So, this is a pair of vacancy. So, this is what happens in case of stoichiometric crystals like sodium chloride, and these are electrically neutral. There are many cases of non-stoichiometric crystals, like one example which is shown over here is a titanium dioxide. So, it is normally it is chemical form TiO2, but very often you will find there are number of there is not enough oxygen atom in the crystal to make it neutral. So, in general you can write this chemical formula of this type of non-stoichiometric crystal like this: TiO2 minus X2 minus X. X of course will be very small. So, in that case what it shows that this type of crystal will be no longer electrically neutral, and this changes the characteristic depending on that magnitude of X, its characteristic, its properties, particularly say its electrical properties or its optical property will change significantly, which is shown over here. So, in this case one of these oxygen atom here is missing. So, if that one oxygen atom is missing, the oxygen was likely to share or take 2 electrons here from titanium. So, basically this 2 electron is in excess. So, basically this electron which actually should have belonged to this atom is now free, and that is shared by all. So, because of this titanium dioxide, when that is oxygen deficient, it is not a stoichiometric exact stoichiometric relationship it follows, in that case it will exhibit conductivity, electrical conductivity. Say if it is pure TiO2, it is insulator, but in a normal cases it is not an insulator. Say if it is oxygen deficient, it is not an insulator, and pure TiO2 you know its color is yellow, it has yellowish tint, whereas if you heat it, you will find you can create some of this oxygen vacancy and then it turns blue, and this is a relatively better electrical conductor. So, that means vacancy changes the properties of material. Now, after this let us look at line defect. So, dimension of a point defect means it is a dimensionless, say only defect is associated or represented, you can visualize it, that it exists at a particular point in the crystal. Now, a situation is little different. We calculated that if a crystal is perfect, that in that case its shear strength, which is shear stress which is required to create a slip step in the crystal, is almost of the order of the shear modulus, or say shear modulus over 50 or over 100, around that, which we do not get in a real crystal. And reason that we do not get is because the crystals contains a defect called dislocation, and this is a line defect. It demarcates two boundaries. It is a boundary between slipped and yet to slip region. Now, let us look at the atomic structures around dislocation, possible dislocations, which is shown here. This is a type of arrangement. So, this is a crystal. So, this is a periodically arranged. See, these atoms are arranged along this line. It is a 2D crystal, say arranged along this line. This is a perfect arrangement. Now, but look at it overall. What you have? You have a missing plane here. In that case, lattices will be little distorted, something like this. This distortion actually represents a kind of a stress field. It's an indication of a stress field. The lattice is strained, and if you try, say, and this line, this point which represents a line, and this line is called dislocation, and this type of dislocation is called edge dislocation, which you can visualize that dislocation to be in a crystal line, in a crystal lattice term, an extra plane of atom here. And now, here you try to describe close this atom to atom circuit, a clockwise circuit, if you want to plot here. So, you move 3 distance this side, 3 distance here, 3 atomic distance here. So, 3 atomic this side, 3 atomic in the opposite direction, and here 3 this way down, 3 atomic space up, you reach over here. So, what you get is you do not come back to the original point. If you do it in a perfect lattice, this circuit will close. So, this circuit does not close. So, that means this is a vector by which this circuit is not closing, and this vector is called Burger's vector. This also we will know that there is a relationship. This Burger vector is also exactly same as the slip vector. Now, this slip vector is pointing in this direction. So, when one does stress calculation, it is quite important to define this Burger's vector, because the stress field or the energy, elastic stored energy of a dislocation will be a strong function of this vector. And in this particular case, when this extra pair of atom lies above the slip plane, this is the slip plane, this is the extra plane of atom above the slip plane. And now, this type of arrangement, here this Berger vector is pointing in this direction, say let us say the positive direction of say x axis. So, this is called a positive edge dislocation. The Berger vector is positive. So, Berger, this type of dislocation, edge dislocation, means where in the crystal you have extra half plane, and this extra half plane lies on the upper half of the slip plane. Now, look at the nature of the stress field. It looks that upper part is compressed. Here you have an extra plane which is compressed together. So, you upper plane half is compressed and lower half, you know, the distances are little more here. So, here lower half you can visualize as if the lower half is under tensile stress. So, if you try to move this dislocation, you can, what you will do, if you do a work, if you do a positive work, this displacement is like this. So, you do a positive work and on the bottom side this it is opposite to the Berger's vector. So, Berger vector is a displacement vector. So, here the work done is negative. So, in a way, to move this dislocation from this end to the other side, you know, you do not spend much energy. So, that is why you, by assuming the crystal that crystal contains dislocation defect called line defect called dislocation, it is possible to explain why the shear stress required to cause slip is so low. So, in reality this stress will not be 0, you have to move this dislocation, that means that it has a surrounding stress field and this stress field will interact with the periodic stress field which is existing within the crystal. So, to move this stress field within a periodic stress field, you will need a small amount of lattice friction stress, which is to be overcome. So, you need, and this stress is much smaller than the ideal strength of the crystal. Now, look at the case of a negative edge dislocation, which is shown over here. So, here the extra half plane is below the slip plane, and here if you try and describe same Berger circuit, you will find that this vector, slip vector or vector needed to complete the circuit, it points in the direction against x axis. If this is x axis, is opposite to the x axis. So, therefore, we call this vector, this is a negative Berger's vector, and we call this dislocation a negative edge dislocation. And look at how does this dislocation moves. To move this dislocation, you have to apply shear stress, which is shown over here. So, this is the extra half plane. So, this is a crystal, not a perfect crystal, the lattices are strained, and here you try and push, apply a shear stress, and when this shear stress overcomes this lattice frictional stress, which resists dislocation motion, then what happens? It moves to the next point, you apply, it will continue, comes here, and finally, you are left with a slip step. So, dislocation moves out of the crystal, leaving behind a slip step, and the magnitude of this slip step is same as that of the Berger's vector. Now, there is another way you can create a dislocation, which is called screw dislocation, which is shown here in this diagram, and you spend a little time to visualize what this diagram shows. So, this is a crystal, imagine, and imagine a plane here. Say let us say that this plane we have sliced, and we are applying shear stress in this direction and this direction. So, on the top and bottom, we are applying the shear stress on the top and bottom in opposite direction, and this is the deformation proceeds like this. This is the boundary, and so therefore, this part of the crystal has slipped, moved one atomic distance forward, only this part has moved one atomic distance forward, that means slipped over this particular plane, whereas this part is yet to slip. So, basically this is the dislocation line, your shear stress is applied along that direction and this dislocation moves perpendicular to this direction. This is the dislocation line and dislocation moves here perpendicular to the direction of the line. But the Burgess vector, the slip vector is along this direction. So, that means Burgess vector here is parallel to the dislocation line. So, the lattice around this point, around this line will be distorted, and which is diagrammatically shown here. If you look carefully, there are two layers of atoms have been plotted, one represented with this dotted line. This is that dotted line, that larger circle. This represents atom lying on the slip plane, and this solid points, this represents atom lying above the slip plane. And what happens? You apply the shear stress. When you apply the shear stress, the top part, top plane has slipped one atomic distance this side. So, these three they have moved here, but this part is yet to move, and in between there is a region where atomic arrangement is little disturbed. So, here these atoms have moved a fraction of this atomic distance, say something like this. So, basically if you look at 3D picture, so basically this atom, if you can visualize this, this atom will be arranged as if along the line of a screw. Imagine a right-handed screw like this, and these atoms are displaced around that in the helical way. Around that they will be disturbed like that. Obviously, this will be associated with a stress field. And here look at that atomic arrangement here. I have tried to draw that, and here also to determine the Burgess vector, you have to construct a Burgess circuit, which is shown over here. So, this part, that arrangement is perfect, possibly here this is perfect, around this there is a distortion here, and this is the slip step which has formed. And here if you try and describe a clockwise Burgess circuit, you will find that you move, the two distance here, here also you move this direction, here 4 atomic distance, here 4 atomic distance, that balances. But here the vertical direction 2 atomic distance, but here is a 1 and here there is a 1 atomic distance. So, when you construct that full 360 degree cycle, you will find there is a slip step, a vector which does not complete the circuit, and you need an additional vector to complete the circuit, and this is in the direction perpendicular to this plane of the drawing. So, basically if we consider this is x axis, this is y axis, if we consider this is z axis. So, this is along the direction, positive direction of the z axis, and this type of dislocation is called positive edge dislocation. In the same way, you can have a negative edge dislocation, where either you invert it like this, you assume that this top part comes forward. Here this top part has gone behind the plane, this top part has gone behind the plane of this drawing, whereas if you imagine this top part, it comes out of the plane towards you. In that case, this slip vector will point in this direction, that is opposite to against the z direction. So, in that case, that type of dislocation we will call a negative screw dislocation. Now, it will be interesting to now let us compare the two. the edge and screw dislocations. Edge and screw dislocations, if you look carefully, two things are happening. See, one, imagine a screw dislocation. So, this is a line which separates this part has slipped, this is yet to slip, this is the Berger vector, and dislocation line will always move perpendicular, any dislocation will move perpendicular to the movement direction will be perpendicular to the dislocation line, and this is the slip vector. In that case, here this is the dislocation line, this is the slip vector, and the angle between this and this is 90, and which you can easily say in a crystal. We will see some example. In a crystal, say suppose if this is a slip plane, you know the Miller indices of the slip plane. So, slip plane will contain, for the dislocation to move, for this to be a slip plane, for this dislocation, the Berger vector and the dislocation direction both must lie on the slip plane, then only the edge dislocation can glide. Now, situation in the case of screw dislocation is little different. Now, this is a screw dislocation, let us say this line is the screw dislocation and this is lying on this plane, but through the and its Berger vector is parallel to the dislocation line. So, therefore, the mobility of this is much more. It can glide on this plane on which it is lying, or it can lie on any plane, any slip plane which is passing through this line. Say suppose when this dislocation moves up to here, so this is a plane which is intersecting along a line parallel to the dislocation line. So, it can now move along this plane also, which is not possible in case of edge dislocation. Edge dislocation will always have a definite slip plane, whereas screw dislocation can move onto another slip plane. It can cross slip. So, from here it is moving along, it can cross slip into this plane. And so, therefore, it is very easy, say suppose to check, say if this dislocation Berger vector is given, the slip plane is given, and it is quite easy to know so which dislocation will be mobile, which will not be mobile. So, let us look at this a little more carefully with respect to, let us say, face centered cubic structure. So, face centered cubic structure. So, basically face centered cubic structure, the slip plane, so face centered cubic structure, slip plane is the plane 1 1 1. Plane 1 1 1 is the slip plane, and we also learned that slip direction is the closed back direction, that is 1 1 0 type of direction, that is face diagonal. Now, look at 1 1 1 1 plane, it has 3 face diagonal. Now, what is the indices of this particular direction? This plane is 1 1. So, this if we assume that this axis is A, this is B, this is C, the crystallographic axis, or we write it x 1, x 2, x 3. In that case, this direction, this is 1 bar, it goes here, from here to here you have to go, you move one step against x 1. So, 1 bar, then 1 along this. So, this is the direction. And what is the Berger vector? Berger vector is one atomic distance along this. So, this distance is from here to here. So, half of this. So, usually, so therefore, if we say that lattice parameter, if it is A, we will say this Berger vector you can write it as A over 2 1 bar 0 1. So, this is a vector representation. If you want to find out the magnitude of the Berger vector, it is quite easy. The magnitude will be, what you do is do for this is 1 square square. So, therefore, this becomes equal to A square over 2. So, this is B square. So, B is therefore, B is A over root 2. Now, check this. Say suppose what is the Berger vector? Say suppose if this we say that this is this Berger vector, can you draw a screw dislocation on this, which is very easy. A screw dislocation is lying along the direction. So, a screw dislocation any direction. So, this if a dislocation on this plane lies along this is a screw dislocation. If a dislocation lies like this, it is a screw dislocation. If it is like this, it is a screw dislocation. But if it has to be an edge dislocation, in that case, this is a direction, it must lie in a direction which is on this, but it must be something like this. So, you visualize this plane. So, this plane will intersect, you intersect this plane along a particular direction, which will be, and this is a direction which lies on this plane, but perpendicular to this, which is quite easy to check. If you recollect that cos theta, the one direction, say a direction say t, whether it lies in a plane n, it is a vector representation, a direction t, a vector t lies on plane n. So, this plane vector, so the best way to check whether they are at right angle. So, you check cos theta, the angle between this and the plane normal should be 90. So, that means this is 0. So, that is T 1 N 1, T 2 N 2, T 3 N 3. This should be 0. So, suppose this plane is 1 1 1. So, this direction it should lie on this. So, this direction, this t should be perpendicular, angle between t and n, this is 90. Say angle between t and the Berger vector, this also should be 90. For then only this will be an edge dislocation. So, you and try and find out. So, therefore, there are not many options. So, basically one option is, say this is Berger vector, this is the plane n, the Berger vector is 1 bar 1 0. So, you can think of a line, say another plane, say which is perpendicular to this as well as here. So, I try this as an exercise, a direction say t, find out the t which is perpendicular to this as well as this. So, one I can say suppose this is, check this, you can do it easily by forming two equation. Another, if you can look at the standard projection, or if you can visualize, so this is a direction, let us say 1, look at this direction 1 bar 1 bar 2. Now, if a direction is 1 bar 1 bar 2, in that case here it satisfies this condition. You substitute it here, it satisfies this condition. Now, does it satisfy the same condition here? You check. So, that means only if that dislocation lies along 1 bar 1 bar 2. So, 1 bar 1 bar 2. So, basically, so 1 bar 1 bar 2 may be some direction, say something like this, which is on this plane, in that case which is lying on this, and it subtends 90 degree. So, that means a dislocation, edge dislocations, to sum up, what we can say, that we learnt about two types of line defect, edge and screw. Out of this, screw dislocation is much more mobile, it can move on several slip system, but for edge dislocation movement is restricted. And next class we will build upon this, and we will see how that concept of dislocation help us to understand the deformation behavior of metals. Thank you.